Hello, my name is Siksha from BSc Chemistry Honors second year. Today we will discuss Clausius Clapeyron equation. When a system is in equilibrium, the free energy change accompanying the process is zero. That is del G is equal to 0 for a system in equilibrium. Further, the variation of free energy with temperature and pressure is given by the total differential equation. That is del dg is equal to vdp minus sdt. Now let us apply the above concept to the physical equilibrium involving the pure substance. That is solid to liquid, liquid to vapor, solid to vapor, and one crystal form to another crystal form. In general, we can say phase 1 to phase 2. Consider the system of temperature T and pressure P. Under these conditions, suppose that free energy of phase 1 is G1 and that of phase 2 is G2. If the temperature of the system is changed from T to T plus dt and pressure from P to P plus dP, suppose the corresponding change in energy of free energy of phase 1 is dg1 and that of phase 2 is dg2. According to equation 2, dg1 is equal to v1 dp minus s1 dt and dg2 is equal to v2 dp minus s2 dt. Here v1 and s1 are the molar volume and the entropy of phase 1, and v2 and s2 are the corresponding value of phase 2. But when phase 1 is in equilibrium with phase 2, del G is equal to 0, that is G2 minus G1 is equal to 0. When G1 is the molar free energy of phase 1 and G2 is that of phase 2 at temperature T and pressure P. Similarly, for equilibrium at temperature T plus dt and pressure P plus dP, we must have G1 plus dg1 minus G1 plus dg1 is equal to 0. But G2 minus G1 is equal to 0. Therefore, dg2 minus dg1 is equal to 0, or dg2 is equal to dg1. Substituting the value of dg1 and dg2 from equation 3 and 4, we get v2 dp minus s2 dt is equal to v1 dp minus s1 dt. On solving, we get del v dot dp is equal to del s dot dt. And rearranging the equation, dp by dt is equal to del s by del v, where del v is equal to v2 minus v1 is the molar volume change and del s is equal to s2 minus s1 is the molar entropy change when phase 1 change into phase 2. If this change occur at temperature T, that is melting point or boiling point extra, and del h is the latent heat of the transformations, then del s is equal to del h by T. Put this value in equation 6 and we get dp by dt is equal to del h by T into del v. This equation was derived by Clapeyron in 1834 and is called Clapeyron equation. Now for the melting equilibrium, that is solid, when solid change into liquid and vice versa, del h is equal to del fh, and latent heat of melting, and T is equal to Tf, the melting fusion temperature. From equation 7, now equation 7 can be written as dp by dt is equal to del fh by Tf into del v. On further, del v, here del v is equal to del L minus VL minus Vs, and Vs is the molar volume of the solid and VL is the molar volume of the liquid. Hence equation 8 may be written as dp by dt is equal to del fh by Tf into VL minus Vs. Now dt by dp is equal to Tf VL minus Vs by del Vh, and where del Vh is the latent heat of vaporization, and this equation gives the variation of melting point with pressure. For the vaporization equilibrium, when liquid change into vapor and vice versa, the Clapeyron equation, that is equation 8, take the form dp by dt is equal to del vh by tb into v minus vl, where del vh is equal to latent heat of vaporization, tb is boiling point of the liquid, vl molar volume of the liquid, and vv is the molar volume of vapor. Remembering that the volume of the liquid is very small as compared to the volume of vapor, so VL can be neglected in comparison to VV. Hence equation 10 may be written as dP by dt is equal to del Vh by T into Vv. Further, assuming the vapor behave like an ideal gas, then we will have PV is equal to RT, where V is equal to RT by P. Substituting this value in equation 11, we get dp by dt is equal to del Vh by RT square into P. 1 by P is equal to 1 by P into dp by dt is equal to del V by H divided by RT square, where d of ln P by dt is equal to del V h by RT square. This equation is called the Clausius Clapeyron equation, as it first derived by Clausius in 1850 during a detailed study of Clapeyron equation. This equation 13 is very commonly written in another form called the integrated form of the Clausius Clapeyron equation, and this may be derived as follows. Equation 13 may be rewrite as d ln P is equal to del Vh by RT square into dt, and if the temperature change from T1 to T2, when the vapor pressure change from P1 to P2, then integrating equation 14 between the appropriate limits, we get integration of d ln P within limit P1 to P2, and is equal to integration of del Vph by RT2 square dot del t within limit t1 to t2, that is integration we doing the integration of equation 14. Now on integrating ln p, we get ln of p ln p2 by p1 is equal to del del Vh by R is constant, and so inside the integration we find 1 by t2 t square dt. On solving, we get v del Vh del Vh by R into 1 by t1 minus 1 by t2. Changing the natural logarithm to the logarithm of base 10, we get 2.303 log of p2 by p1 is equal to del del Vh by R into t2 minus t1 by t1 t2. So then we get a log of p2 by p1 is equal to del Vh by 2.303 R into t2 minus t1 by t1 t2. This is called the integrated form of the Clausius Clapeyron equation. Now the application of Clausius Clapeyron equations are, this equation is useful in number of ways. For example, first, if the vapor pressure of the liquid at two different temperatures are known, and the latent heat of vaporization of liquid can be calculated. Second, if boiling point of a liquid is known, at some particular pressure, the boiling point at any other pressures can be calculated, provided the latent heat of vaporization of the liquid is known. If the vapor pressure of a liquid is known at one particular temperature, the value at any other temperatures can be calculated if the latent heat of vaporization of the liquid is known. That's it. Thank you.